So this presentation outlines the technical roadmap to that 30-year goal. As you see in this wireframe diagram, the hearth is the absolute thermal epicenter where temperatures and chemistry meet a structure. Historically, campaigns lasted 10 to 15 years, but through the evolution of material and very much improvised monitoring and at present the involvement of AI and ML, the refinement in monitoring also contributed towards achieving this target much easier way. So we have doubled that expectation today with the help of material as well as monitoring. Today we will look at the engineering and discipline required to protect this critical asset. So to understand our goal, we must first look at the difference between a failed hearth and a managed one. So understanding of this slide will gives us a lot of insight regarding further course of action. So looking at the contrast on this slide, the diagram on the left uh, is the nightmare, a catastrophic breakout. Notice the red hot metal breaching the cracks that represent massive safety risk and economic loss. It's a big issue, a catastrophe we can say. Now look at the right. Look at the right. Uh, this is our target: thermal equilibrium and optimized fluid flow. That is, by maintaining a structural integrity above 95%, we keep the furnace in the safe zone for 3 decades. So maintaining that safety depends entirely on the specific boundary, the 1150-degree isotherm. So if you look at the thermal map, the orange dashed line is our target, that is point specifically to the 1150 line. Now 1150 degrees Celsius is the solidification point where liquid iron turns into solid steel. So we want to push this line as far away from the shell as possible by pulling heat through the high conductivity carbon refractory to the water cooled cell. So we built a protective skull of frozen iron. Essentially, the iron builds its own wall before it can consume the refractory. So to pull that heat out fast enough, we need brick that conduct heat like a highway. So if you look into this chart tracks 60 years of brick evolution. So as you can see these bar graphs. So notice the thermal conductivity line. We started in 1965 with generation 1 block at 17.1, and today generation uh, 6 blocks hits 37. So from 37 to 17 to 37, more than double the cooling power. So this unmasked thermal dissipation combined with the titanium carbide additive promotes the localized freezing of a viscous, that is titanium bare layer, directly on the hot face. So while high conductivity carbon is the goal, we often use a secondary shield for the first decade. Now coming to the modern design, use a ceramic cup as a buffer for the first decade. If you look at the diagram, as you can see, phase 1 is the first life where this mullite or high alumina layer protect the structural carbon from the thermal shock and the initial chemical erosion. Thermal shock and chemical erosion. So it can act as an energy saver by reducing heat loss. Once the ceramic is sacrificially consumed, we enter phase 2, which is the next diagram. The second life, where the generation 6 carbon cooling defenses takes over to maintain the skull. So even with the good brick, we have to manage the physical flow of the iron itself. So we use erosion ships to tell us what's happening inside. These ship on the left, as you can see here, these are the very critical threat. This shape on the left side is the critical threat. It is caused by a sitting dead man that blocked the center, forcing the hot metal to scream around the edges at high speed, undercutting the sidewall block, creating a elephant foot shot of impression. On the right, the bowl shape is manageable. This happens when a floating dead man opens a central passage, shifting weir safely away from the walls towards a thick center bottom. Now, physical wear is one thing, but we also face a silent chemical killer, and that is also important. So, these aspects also to look into. Zinc and alkalis, really the two killers component are like slow motion explosive for the bricks. I again stress upon slow motion explosive for the bricks. So the vapors drive into the bricks' teeny pores. As the temperature drops, they react to form zinc oxide and silicate. That reaction causes a 57% volume expansion, as it is also denoted in the slide very clearly. This massive internal pressure detonates the carbon matrix from the inside, forming a thermally dead, crumbly brittle layer that retains conductivity and structural strength. Almost it create a catastrophe, a disaster for the carbon refractory. And once carbon refractory damage, that means the life of the hearth is comes to zero. So to stop both chemical and physical wear, we must master the force balance that keep the dead man floating, and this is really very much important. Floating the dead man is a game of physics, and on the left we have a burden, weight and downward gas track pushing down. On the right we have a buoyancy of liquid iron at 7.8 grams per cubic centimeter, and slag or operational lever is permeability. By charging large center coke, we reduce the gas drag. When buoyancy wins, the dead man lift opens a coke-free zone at the bottom to protect the wall. So maintaining this floating state with the help of balancing of these multidimensional forces which maintain this floating state, and also we need to require a balance discipline tapping. So tapping discipline is also very important. It is the operational mastery which meets longevity. So look at the full pull graph. Keeping iron in trough prevents thermal shock and prevents iron from backing up into two-year slowdown. We also have to choose our taffle length carefully. A short taffle creates a fast edge flow that uh, scores the wall, but a long taffle draws iron safely from the slow moving center. So always match your drill bit size precisely to your production rate. So if you do see wear occurring, we have an active way to heal the lining. Titanium is our hero technology, as we have seen in past also through many of the presentation and with sharing the thought with our colleagues. For the hearth. That is, titanium is our hero technology for the hearth. So we inject our chains titanium bearing material like ilmenite, and the TiO2 reduces and react at extreme temperature to form titanium carbonitride. So these compounds have a massive melting points of 3140 degrees Celsius. They precipitate out and stick to worn areas, forming a viscous titania beer, the frizz layer that patches eroded carbon. So, to execute these strategies, we need to see through the steel shell. We no longer guess what about heart thickness, we measure it. On the left, the MEUSA thermal mapping model uses thermocouple arrays to map the 3D position of that 1150 degrees line. On the right, as you can see, uh, a sacrificial ultrasonic waveguides, and these use continuous pulse echo tracking to determine actual wear in real time with over 98% measurement accuracy. So this precision allows for data driven decision on production rate. So the future is moving from real time monitoring to predictive AI. This digital twin is the cutting edge of the industry. We use LSTM neural network to forecast thermal indicators like hot metal temperature hours before attack. Simultaneously, light GBM machine learning estimate the thickness of the invisible slag layer on the cooling plates. We no longer wait for a thermocouple to spike. The digital twin simulate the erosion before it even happens. While technology improves, we face a massive new chemical challenge. And one of them is hydrogen. Hydrogen, as you must be knowing, is a really very revolutionary talking terms in field of particularly decarbonization. And in decarbonization, we rewrite the rules of earth chemistry. So as we inject hydrogen to lower coke rate, we create highly reactive atmosphere. So looking at this equation, hydrogen react with silica in our refractory to form gas and water. And these silica laws very aggressively degrade the mullite and high alumina ceramic cup. So furthermore, hydrogen reduction is endothermic, it suck up heat, shifting our thermal zones and making slack control even more complex. So, how do we pull this all together for a 30-year life? So, this becomes a very interesting barricade, challenge, barrier, we can say. So, coming to the this slide, which is all about uh, longevity estimated estimation. So longevity is not just about choosing one good brick, it is about continuous daily mastery of a balanced ecosystem, and which is very nicely shown in this slide. So these are our five pillars which is shown in the slide. High conductivity generation, 6 design, the 10-year ceramic cup shield, titanium chemical management, maintaining permeability to float the dead man, and using AI or digital prediction. So when these five work in harmony, the 30-year campaign moves from a dream to an engineering reality. So this mastery is the foundation for the future of our industry. So in conclusion, the hearth is the foundation of global low carbon steel. By mastering this ecosystem today, we guarantee our readiness for the decarbonized future of iron making. We have the material, the chemical strategies, and the digital tools to reach 30-year safety and efficiency.